is big data in our previous session. The agenda for today's class is we are going to discuss about the architecture of Hadoop. What is Hadoop and its associated architecture in terms of Hadoop 1.x and in terms of Hadoop 2.x. And second part, we are going to discuss about these daemons. And its functionalities. What are all the functions associated with Hadoop daemons? And in third part, we are going to discuss about Hadoop ecosystem components and need of those and the functions of those ecosystem components. This is the agenda for today's session. Okay. So in our previous session, we have gone through what is big data. And we have, at the time of discussion of big data, we had a comparison between big data and RDBMS. So in terms of the key characteristics, volume, velocity, variety, veracity, and in terms of its database architecture. So centralized architecture versus a distributed database architecture, and in terms of infrastructure, client server architecture versus master slave architecture. These are all the things that we have kick-started in our previous session. Okay, now we are going into this architecture of Hadoop. So all you people are aware that so why we need to go for this Hadoop? So because of lagging in this RDBMS. So for as of our knowledge, for data storage and processing, we go for this RDBMS like Oracle, MySQL, SQL Server, etc., etc. RDBMS is lagging in several sense. First, in terms of volume, the amount of data that we can store and process is up to terabytes. It's work fine. Whereas if we go beyond terabytes, such as petabyte and zettabyte, your RDBMS couldn't able to support this much of workload. So also because of its centralized database architecture, you have only a single server. On top of it, you need to store the database. You can't able to scale the database beyond the server's capability. To what extent that the server support a maximum capacity, to that extent only you can store your primary data. If your database size increases, here you want to go for architecture called as a storage box like a NAS box or a sandbox, network attached storage or storage area network. But transferring your application may be running here in your database server, your data may be here, and whenever the data is needed, the data need to be bring into the server where your application is running. In this case, your application is rigid, fixed. Your data moves towards the server where you have application. If the data that you need to move is small in size, if it is a gigabyte, then it's work fine. Whereas since in big data, we are dealing with the terabyte and petabyte, moving a huge volume of data from one device into this server will be a time-consuming process. Therefore, this is not a best suited solution for big data. That is the second thing in terms of volume. Velocity, so to how much of request that is approaching the server, that is velocity, that is the rate at which the data has been generated has been termed as velocity. So it supports a gigabyte per hour. If the data generation speed is gigabyte per hour, your RDBMS support. Whereas in terms of big data, what you called as big data, we need terabyte, petabyte of data generation. So for example, if you take a Facebook, in our example, we have referred to Facebook. In our Facebook, per day it is generating almost 500 terabytes of data per day. If you take into per hour, at the average it generates 25 terabytes of data. Similarly, Twitter, per hour it generates around 5 terabytes of tweets. So if this much of data is approaching the server, then the server, if it is RDBMS, it couldn't able to accommodate this much of workload. That is the second characteristics, velocity. And the most important characteristics in terms of variety has been RDBMS support only structured data, whereas we have discussed about semi-structured data, unstructured data like audio, video, and other things. Semi-structured data. like your PDF, emails, and documents. Okay, so here your RDBMS support only structured data, and whereas your big data need to support all the above set things, semi-structure and structure and structure. If you took into consideration today's digital information, so almost 20% of data comes under structured data. Remaining 80% of data that you need to store and process, because everywhere has been computerized. We have instrumentation, we have sensors, we have RFID devices. Everywhere we are debuting computers, which is going to replace human in the near future by means of artificial intelligence and machine learning. One of the most wanted thing today is in IT industry. Okay, machine learning. So everywhere we being debuted machine, the data that we need to store and process, 80% of data comes under unstructured data and semi-structured data. Whereas our RDBMS have a support only for structured data. That is the third difference that we have discussed. And in terms of veracity, how far our data is reliable, to which extent the data is reliable. If it is RDBMS, you need to have very clean data. Whenever data get into this RDBMS table, it will check against this schema. If the data violates the schema, the data won't be permitted into the RDBMS table. Whereas in case of big data, since we are crawling data from real world entities, such as it may be a social networking sites, it may be a sensor, or it may be IoT data from IoT devices, we can't able to ensure a pure data without any anomalies like missing value, inconsistency, irrelevancy. So here those data need to be accommodated, and laterly while processing it should have a provision to clean the data. So that feature has been termed as veracity. So these are all the things that we have discussed. Okay. So any doubt with respect to our previous discussion? If yes, please let me know. And once I clear that doubt, we can proceed further. Else, we can proceed with our today's agenda of architecture of Hadoop. So because of the above said drawbacks, we have a data appliances. We have a component called data appliances. So RDBMS does not have the support for storing and processing what we call as big data. So we have data appliances. What is data appliances? Sophisticated hardware with some customized software. Okay, so it is intentionally for storing and processing what we call as big data. This has been designed to support big data, such as we have several data appliances, such as Teradata, Exadata by Oracle, and we have a Greenplum by IBM, Greenplum. So I may have a spell error, please forgive. And we have a Netezza. So these are all some of the Teradata. If you go up with these details, you can find out. Data appliances will let you know what it is. Data appliance. They are all very sophisticated higher-end devices. Now we have Oracle Big Data appliances. So which is coming here equipped with everything, almost all sorts of data streaming, data capturing, storing and processing, visualization, everything that you can do on a single system itself. Okay, but what are all the things that is not supported in RDBMS is supported in this architecture. We have several data appliances such as Teradata. Okay, it belongs to Oracle. Okay, these are all appliances, higher-end sophisticated higher-end servers, which performs all the above set activity. Okay, so we have a data storage up to terabytes and petabytes. We have a large number of computing. We have a storage, memory, everything. What are all that we are looking for in terms of storing and processing big data perspective is applicable here too. Okay. So, but the drawback associated with the data appliances is cost. Okay, it need to invest in terms of crores to procure these data appliances. That is the drawback associated. Even though these data appliances are able to store and process big data, the drawback associated with these data appliances are cost. In terms of hardware, you need to invest in terms of crores. A fully populated data appliances will comes with 1 or 2 crores. And in terms of softwares, being it is a customized software, they are licensed softwares. So you need to pay according to your utilization. So how much of data that you are storing, accordingly you need to pay for. These are all the drawbacks associated with the data appliances. But if you take some countries, developing countries like India, out of which 100, nearly 70-75% of companies are either a startup company or coming up in the following category: startup company, a small level or mid-level enterprise. Okay, they are not very big companies like Wipro, TCS, and Infosys or Reliance. So around 20-25% of companies comes under enterprise category. So, but if it is 75% of companies coming under this category, this is not at all affordable for them to invest in terms of crores for infrastructure. So, for the company, they have data of the above caliber, what they are looking for devices like data appliances. But in terms of investment has been concerned, they have a very less capital amount. So what they will do? So here comes a messiah from Apache Open Source Foundation. OSF. Apache Open Source Foundation developed a tool called as Hadoop, the open source tool. We call this Hadoop as a framework. It is a set of several components. Okay, it is a combination of several things. It is not a single entity. For data crawling, we have some set of components. For data storing, we have some set of components. And for data processing, we have some set of components. For coordination, we have some set of components. For task automation, we have a set of components. So togetherly, we call this as a Hadoop framework. Hadoop was initially developed by Apache Open Source Software, okay, which is open source. It was developed using Java as its programming languages. Okay, it is developed using Java as its programming language. It implies the concept of distributed computing. So both in terms of computation and both in terms of data storage, it is distributed database and distributed computing. Then the most important thing is we can make use of commodity hardware. So no need to pay for in terms of crores as that you need to invest for data appliances. All the associated hardware are commodity hardwares. So commodity hardware means low cost hardware. You can go up with i3, i5, i7 like machines for your data storage and data processing. And all the associated softwares are open source softwares. Okay, you no need to pay for even a single paisa. But all the softwares that is associated with Hadoop comes with the open source software. Okay, the problem that we have faced with the data appliances in terms of cost, a huge cost in nearing to crores, and the software license software has been eradicated here by means of debuting a commodity hardware and open source software. So these are all some of the key points associated with this Hadoop. Now we move on to discussion of this Hadoop framework. Okay. Okay, so Hadoop is an open source software. Okay, this consists of two core key components. One is HDFS and second one is MapReduce. HDFS stands for Hadoop Distributed File System. So you are aware that Hadoop is a distributed database architecture. Okay, what is distributed database architecture? How it differs from centralized? We have already discussed. If it is a centralized database architecture like RDBMS, you have data stored only on a single server. So that server we call it as a backend. Okay, so how a user can able to access? User through a client, the computer through which user interacts, it's called as a client. And we have a front-end software using which user can interact with the data stored at the backend. We have multiple clients. Okay, we have client 1, client 2. We have multiple clients. Each and every client will facilitate the user interface. The user can submit a query. Here the query will be processed on the server. The result will be returned back. Here the key thing is that your data storage and data processing both takes place on the server. This client simply acts as an interface. This is the architecture currently followed, that is centralized database architecture. Whereas in case of this distributed architecture, we have data stored across multiple servers, not on a single server. Okay, so we have several computers under which data has been stored. The computer where we store data in Hadoop has been termed as data node. We have data node 1, data node 2, n number of data nodes. Okay, we call this as data nodes. Here the data will be distributed across again these data nodes. For example, So if you want to store 10 TB of data, let me imagine each data node containing 2 terabyte of storage. Here what happens here in this case, this 10 TB of data has been splitted into chunks. So I am talking a layman point. So real time the data will be stored in forms of blocks that we will discuss. So here the data of 10 TB, let me take a file 1 whose size is 10 TB. So if the file 1 need to be stored here in our Hadoop, means across this data node, imagine we have 5 data nodes. So each data node capacity is assumed to be of 2 terabyte each. So what happened here in this case, the 10 TB of file has been split into a chunk of 2 TB each, and each 2 TB will be stored on a particular data node. Okay, each 2 TB will be stored on a particular data node. Here the data has been distributed. Let me take this 10 TB contain 10 lakhs of transaction data. Okay, so here this each data node in this case contain 2 lakhs of transaction. 2 lakhs of transaction. For our assumption, I am making it. Okay, in really it will be in forms of blocks of size 64 MB and 128 MB that we will discuss. So here the data of 10 TB has been distributed across these 5 data nodes. Each and every data node will have a partial data. Okay, so this is called as a distributed database. Okay, who will responsible for splitting and who will responsible for deciding under which data node data need to be copied will be discussed later. Okay, so here it is not the responsibility of the administrator or the developer to decide these things. The Hadoop framework itself, with the help of a computer called as name node, will decide how to split the data and how to store the data, how to ensure high availability of the data. Everything will be taken care by the Hadoop framework itself with the help of a computer called as name node. Okay, that we will discuss now. So this is the, whereas if it is a centralized database processing, so all these 10 TB of data need to be stored on a particular server. If the server does not have a capacity, then we go for a storage box like NAS box or SANbox. You may aware of what is NAS and SAN. It is a bunch of disk. If not, I will let you know how it will look like. Okay, so here it is essentially meant for storage purpose. EMC's storage. Okay, there are several companies, EMC, Netisa, these are all hard disk, bunch of hard disk. Okay, so here in this case, you have each hard disk maybe of capacity. So you may have your server here. Okay, so your server may be containing this application and data may be stored in this. These are all hard disk. Okay, these are all hard disk. This is an example of a NAS box, a network attached storage or a storage area network. So whenever you need a data, the data need to be bring into the box. Okay, so this is what here in case of RDBMS, the huge volume of data can be accommodated. But the thing is that, so transferring data, huge volume of data. For example, if you want to copy a film which occupies 3 GB from your computer into your pen drive, how much of time that it takes? To copy a film size of 3 GB, it took around 3 to 5 minutes. So imagine if you want to copy 3 terabyte, how much of time that? It 2000. It runs into hours. Okay, so it is not at all a better solution in transferring terabyte and petabyte of data by storing into a box or into the application. Okay, so we need to store the data in the server itself for processing to facilitate very quick processing. So because of that, the architecture here followed is not a centralized architecture. The architecture here followed is a distributed architecture. Okay, so here in terms of this Hadoop architecture has been concerned. So Hadoop comes with the following architecture: a master slave architecture. Here some computer has been designated as masters. What are all those computers? We have name node, a computer called as name node. We have a computer called as a secondary name node. We have a computer called as job tracker. They are all masters. Okay. Then we have a data nodes. The computer called as a data nodes. And on top of data nodes, we have a task tracker. Task tracker is a process running on top of the data nodes. Okay. So this is the architecture associated with Hadoop 1.x. So here, out of this computer, the name node plays the key role of the Hadoop cluster. So what is cluster? A group of computer, we call it as a cluster. Here the architecture will be, you will be having only one name node, you will be having only one secondary name node, you will be having only one job tracker. It is mandatory in this architecture of 1.x. You can't have more than one name node, or you can't have more than one job tracker. And you may have multiple data nodes. The number of data nodes, you may have n data nodes. Which factor determines this data node? So you may have n data nodes. Two factors you want to take into consideration in determining the number of data nodes in your cluster. The first factor that you need to take into consideration is how much of volume of data that you need to store. Okay, let me make it in a separate slide. So here the number of data nodes in your Hadoop cluster. Cluster is nothing but a group of computer, we call it as a cluster. Being we have several computers here, we call this as a Hadoop cluster. We have name node, secondary name node, job tracker and multiple data nodes. We call this as a Hadoop cluster. Okay. So here the master nodes, the name node, the secondary name node, the job tracker nodes, we need to have only one. You can't have beyond this. Whereas here, the data nodes, you may have n data nodes. Data node 1,
excuse me, sir,
data node 2, up to n data nodes. Okay, this is your cluster. Hadoop cluster.
hello.
Yes.
Sir, these are all we have taken.
Okay. So here, how data is going to be split, like we are going to discuss. Here, how a user interact with this cluster. We have a component called as HDFS client, through which the user will have an interaction. We have a component called as HDFS client. HDFS client through which user will have an interaction. So please wait a while, I am having a... Yes, we have a separate computer here too, we call this as a HDFS client. Okay, so in this client computer what we need is, we need to have Java. It is recommended to have JDK 1.7. And here we may have installed Hadoop, or we may not need to install Hadoop. Okay, it is optional. I will let you know where you need to go for Hadoop, where we didn't need to go for Hadoop. This is an interface through which user can submit a job. If a user wants to submit a job, or if the user wants to perform a write or read any data into this data node Hadoop cluster, so this is the system through which the user interaction takes place here. Here, all the hard disk associated with these data nodes will togetherly form this HDFS, Hadoop Distributed File System. You are aware of what is a file system. A file system is one which let us know with respect to each and every operating system how to organize data. For example, Windows is following the file system of FAT16, FAT32, NTFS, etc., etc., under which we have a hard disk partitioned with respect to C drive, D drive, etc., under which you have directory, under which you have subdirectories. Okay, we have files organized under this manner. Similarly, if it is a Linux, we have this file system of Linux is having extended file system, ext2, ext3, ext4, NFS network file sharing. Okay, similarly, being we have this Hadoop as a distributed database, how to split and how to store the data across these data nodes will be governed by a file system called as Hadoop Distributed File System. It let us know how to split and how to store data in a distributed manner. This is the HDFS will deals with the data storage part, where the data will be stored. Here the data will be stored and data will be processed only on these slave nodes. They are all masters. The nodes that is listed on this upper top is master, name node, secondary name node, and job tracker, and these nodes comes under slaves. So in data node, we have task tracker, a daemon. How many task trackers will be there? It is equivalent to that number of data nodes. So in this Hadoop cluster of 1.x, it is mandatory that we need to have only one name node, one secondary name node, and only one job tracker. Beyond that, you can't have more than this. Then we have n number of data nodes. The number of data nodes depends upon two factors. Okay, what are all those two factors? First factor, it determines how much of volume of data that we need to store. And the second thing, the hard disk capacity of your data nodes. For example, if you want to store 10 TB of data, and with the hard disk capacity of data node is assumed to be 2 TB, in this case, we need 5 data nodes. Then if it is a 20 TB of data, so in this case, the same with the 2 TB of storage, we need 10 data nodes. Okay. So here, the concept here followed by Hadoop is horizontal scaling. What do you mean by scaling? Scaling means adding the additional resources. Imagine you have a single server environment with one microprocessor and 1 GB of RAM. So it may be a web server. So here with this above equipped hardware, it support, let me make it 1000 user requests per second. If the number of requests increases beyond that, for example, if it's 1100 or 1200, it can able to withstand the load to some extent with a little bit degraded efficiency. Okay, if the number of requests increases to 1500, it couldn't able to withstand this much of workload. So what happens here in this case? The server being it couldn't able to tackle this workload, get caught with panic and it will down. So how to resolve this? You need to add additional resources. You need to add additional one processor or 1 GB of RAM instance. Then here now server now equipped with 2 microprocessor and 2 GB of RAM. So now it can able to withstand up to 2000 requests. If the number of requests increases beyond that, let me make it to 2500. In this case, what we need to do, you want to add additional 1 microprocessor and 1 GB of RAM. The process of adding the resources to maintain the efficiency of a particular server is termed as scaling. Here the scaling, we come across two types of scaling. One is vertical scaling. Second one is horizontal scaling. So vertical scaling in sense, within this server itself, we add resources, 1 microprocessor plus 1 microprocessor according to your requirement. But the drawback associated with this, so you can't go and add the resources to a server. Why so? Because the server is limited with this capability, the number of slots which support the n number of processors. If a server support only 4 processors, if it has only 4 processing slots, and if it contains only 3 RAM slots, beyond that you can't able to extend. You need to go for procuring a new server which facilitates additional components. So this process is called as vertical scaling. This is the drawback associated with vertical scaling. So we go for a concept called as horizontal scaling. In this, rather than adding the resources, we add additional servers. So you can go and add the server. A server with 1 microprocessor, 1 GB, you can go and add with the same configuration. Whenever the data size increases, you can scale with the new server. This concept is adapted by Hadoop. Hadoop follows the concept of horizontal scalable. Okay. So here, in this sense, if you have 10 TB of data, in this case, we have initially 5 data nodes will be configured. Data node 1, data node 2, up to data node 5 will be configured. If the volume of data increases from 10 TB to 20 TB, no need to worry about that. What we can do, you can further expand your cluster by adding additional 5 data nodes. Now we have 10 data nodes. If the data size increases to 50 terabytes, no need to worry about it. You can go and add the data node. Now the number of data node will be 25 in number. So you no need to bother about the increased workload in this case. According to your workload, you can go and add the server. Okay. So here we come several companies make use of the infrastructure rather than going for the physical infrastructure. They are getting the infrastructure from a cloud, a public or private cloud like Amazon, AWS or Azure cloud. So what is the advantage in going for that? If you have 5 data nodes, if your load suddenly increases to 20 terabytes, you need additional 5 data nodes. If it is a physical cluster, it is not at all possible. If it is a physical cluster, it is not at all possible. You add additional 5 data nodes by procuring and configuring and attaching with the existing node. So if it is a resource that you acquire from cloud, if it is a cloud-based instance, within a minute, you can automatically add the additional resources. If you feel now you have 25 data nodes, now the data size is 50 terabyte. If the volume of data that you need to process suddenly comes down to 10 terabyte, so in this case, how many data nodes that you are interested? You are interested only 5 data nodes, but we have a surplus of 25 data nodes. 20 data nodes is almost not used. They are in ideal state. If it is a physical server, you can't do anything. If it is an instance from cloud, what you can do? You can release the underutilized resources. If you found that the number of clusters, number of servers in your Hadoop cluster is more than what we are in need of, you can release those unwanted resources. Here, the process of adding the resources whenever it is need is called as scale up. The process of releasing the unwanted resources is called as scale down. Okay, so this activity can be automated. Scaling up and scaling down can be automated by using a service from Amazon Cloud called as auto scaling. So we have included cloud in our curriculum to facilitate the architect and administrators. Also because profile with Amazon or Azure cloud with Hadoop in terms of architect and admin perspective is most demanded. So you will know how to create a machine and how to configure a Hadoop cluster using Amazon cloud in our curriculum. We use EC2 and we also make use of another service called as EMR, which is a distribution of Amazon, Elastic MapReduce. At that time, I will have a discussion on how it can be scaled up and scaled down using this auto scaling. Okay, this is an additional benefit in our curriculum. Okay, we will also have a minimum of 5 to 6 hours will be devoted for letting you know the concept behind configuring your Hadoop cluster in Amazon cloud. Okay. So this is the way by which you can go on add your data nodes according to your current workload. So here the intention behind this discussion is I want to make you aware of what is scaling and what is the scaling methodology followed by Amazon. What's the drawback associated with vertical? How this Hadoop cluster can able to withstand the increased load by means of horizontal scaling. How the data will be split, what is the block? Now we are going to discuss. Before proceeding further, if you have any doubt with respect to what we have discussed, please. Okay, so now you know how many name nodes, how many secondary name node, how many job tracker in your Hadoop 1.x. It is mandatorily only one. Then you have n number of data nodes. Okay, the n number of data nodes depends upon the following two factors that you know. So now we are going to discuss about the functionalities of each and every demand. Before going into these functionalities of each and every demand, I will let you know how the data will be stored. Here we make use of the concept called as blocks. Okay, so if you have a aware what is block? Block is the basic unit of storage. Whether it is operating system or is a database, the basic unit of storage is blocks. In terms of OS, let me take a Windows or Linux OS, the block size may be 4 KB. In terms of database like Oracle, the default block size is 8 KB. You can have 16 and maximum of 32 KB. So here, if you have a file, let me make it a file of 1 MB, the file will be divided into blocks. Okay, so the block size will be of 8 KB. Here, in case of this Hadoop, if it is 1.x, the block size is 64 MB in terms of MB. If it is 2.x, the block size is 128 MB by default. You can increase the block size according to your requirement. So this is the default block size. So here, why this much of size? Also, here in case of your traditional RDBMS, we have in terms of KB, and the block size is in terms of MB. Let me make it a file dot text. Okay, whose size is 1 GB instance. If we have Hadoop 1.x, this file will be divided into block size of 64 MB, 64 MB each. Okay. So how many blocks will be there for a 1 GB file? Can you please let me know, anyone? How many number of blocks that we need to store for Hadoop 1.x and Hadoop 2.x if you follow the default block size? Anyone? So 1 GB equivalent to 1024 MB. Therefore, being the block size is 64, it comes around 16 blocks. Okay, you will be having 16 blocks only. Yeah, good Abhilash, good. Then if it is 2.x, it will be only 8 blocks. So, who will responsible for managing all those things? It is the name node. The name node is the master. It is the king of the cluster. Okay, so the name node will maintain all this information. Okay, so we then the role of a name node here is it maintains the metadata information about the cluster, entire metadata information. How many data nodes are there? How many users are currently working with the cluster? How many files are there? What are all the blocks associated with the corresponding files? Where the blocks has been stored? How many processes that is currently running? How many blocks are corrupted? So all those informations will be managed by the name node. Okay, so here imagine if the block size of 64 MB, you need to maintain 16 blocks. If it is in terms of KB, imagine how much that you need to maintain. If it is in terms of KB, so here 16, for example, if you imagine that Oracle, if you want to store 1 GB of file in Oracle, so how much of thing that you need to go for? So here 16 into 1024 into 8. This much of blocks that it need to be splitted if it is in terms of KB. So number of blocks and associated information a name node need to maintain will be very, very large. And it will become a bottleneck for a name node if it need to handle terabytes and petabytes of data blocks. That is the reason why it is architected in such a manner that the block size will be of in terms of megabytes, not in terms of KB. Being your Hadoop is dealing with handling terabytes and petabytes of data, so we need to maintain a block size in terms of MB. So as a result, the number of block related information that is need to be maintained by the name node will be less in number and it won't be get caught with any panic. So that's the reason why we have this much of block size. How a data has been stored, let me discuss now. So imagine we have 5 data nodes: data node 1, data node 2, data node 3, okay. You have a file.text, we make it, the size is 192 MB. Okay, a small file, a transaction file. Here with Hadoop 1.x, the default block size is 64 MB. Now the file has been divided into blocks, 3 blocks. How many blocks? Block B1, block B2 and block B3. Each block size is 64 MB. And how the block is distributed? Block B1, B2, B3. Across these nodes it will be distributed. So imagine now you have a file with 192 with a block size of 3 blocks. So this information will be managed by the name node. Okay, the name node will maintain this information. Here file.text whose size is 192 MB. This contains 3 blocks. The owner of the file is Ram. Okay, the data node which holds the blocks are data node DN1 holds block B1 and block B2. Data node DN2 holds the blocks B3. So this information we call it as a metadata, MD. This is managed for all the files and for all the user, for all the jobs by the name node. Where it manages the information, the name node manages the information in its RAM memory, not on the hard disk. Under 2 files, the name node will have 2 files. One file is FS image, file system image. Another file is edit log. So these 2 files will hold the metadata informations. Okay, what it will be managed in FS, what it will be managed in EditLab, now we will discuss. So at the initial time, during the start of a cluster, the metadata information initially will be stored in the FS image, and if there is a modification in the cluster, if there is a modification, those modified information, the updated information, the changed information will be stored in the EditLab. Okay, the original information will be in FS image. Whenever there is a change in the cluster, what sort of change, I will let you know what change will be happen. So imagine you have your data stored across these data nodes. Your data node DN2 gets stuck with. Okay, so since we are having commodity hardware, we have discussed that you may have a commodity hardware for the data nodes. You may have a computer with i3, i5 like machine. You may have a commodity hardware. Being your commodity hardware being it is frequently subjected to failure, you can't able to ensure high availability of your commodity hardware. Okay, so in this case, what happens? Let me imagine a scenario. Your data node DN2 get crashed. In this case, what happens here? In this case, your block B3 will be low. You will be losing your block B3. Imagine you have a 30,000 records in this 192 MB with each block containing 10,000 records. So if you lost your data node DN2, then this 10,000 records associated with block 3, you won't, it will be lost. So here this is not a recommended solution. Therefore, what Hadoop recommends here is to ensure high availability of your data. So it goes for a concept called as block replication. It goes for the concept called as block replication. It recommends minimum 3 replicas. It recommends minimum 3 replicas. Okay. So each and every block, being we are storing in a commodity hardware, and the commodity hardware you can't able to predict at what time a hardware will fail. If you have only one copy and if a hardware fails, it may result in a loss of information. To overcome from that, it goes for the concept of replication. Hadoop recommends to minimum to have 3 replica of a particular block. That means a block need to be stored minimum at 3 locations. Let me make it B1, B2, B3. Okay, so B3, B1 and B2. So in this case, each block B1 1 2 3, B2 1 2 3. Okay, we have 3 copies. If we have this replica, so if this data node DN2 fails, you no need to worry about that. Why so? Because we have a copy of block B3 in data node DN3 and data node DN4. Similarly, we have the copy of B1 and B2 in data node DN1 and data node DN4. So you can continue your business without affecting failure of a single data node or more than one data node won't result in the business discontinuity. So it recommends minimum to have 3 replica. Is it mandatory? No, it is not a mandatory solution. It recommends if you want to have 5 replica, if you want you more reliability to your data, you want 5 replica, yes, that is possible. No, I only want 2 replica, that is also possible. No, I want only 1 replica. My data is not has need as okay. If I lose the data, I can restore the data. If that is the case, you can have 1. So, but the minimum recommended replica is 3 replica. So at any point of time, you need to maintain 3 replica by default. Okay, so now this is the way by which you can ensure a high availability in case of a failure to the data node. So what happens when a data node fails? What sort of action a name node will initiate when it detects the data node failure? Now we are going to discuss. Okay, now the blocks, you know, the data is divided into blocks. The block size is the default 64 MB, and the block will be distributed across these data nodes. If you have only one copy, then if a data node fails, you will lose the information. To overcome from that, Hadoop recommends to go for a concept of block replication. It recommends to have minimum 3 replica. These blocks will be distributed in the following manner. So if a data node fails, you no need to worry about that. By making use of the remaining copy, you can continue your activity in your Hadoop cluster. This is the way by which you can ensure high availability in your Hadoop cluster by making the concept of block replication. Now we are going to discuss what action a name node will initiate whenever it detects a data node failure, How it will identify a data node failure? So what sort of information will be stored in edit log once a data node failure is identified by the name node? Let me go for a break for 10 minutes and we. So now we are going to discuss about how a name node came to know the failure of data node and what action that it will initiate if it found a data node to be failed. Okay. So here in this case, if the data node DN2 fails, now the blocks associated with this data node B3, B1 and B2, now instead of this 3 replica, we have only 2 replica of this block, only 2 copy of the block. So this scenario is called as a block under replication. This is an interview question. Block under replication or under replicated block. We call this as a under replicated block or block under replication. Please make a note. So because of the above said failure, then here in this case, instead of being maintained 3 copy, these blocks will be only having 2 copies. So we call this as a under replicated block. How this under replication will be resolved? What sort of action a name node will do? We are going to discuss now. Okay. Now, each data node for every 3 seconds once, each data node will send a heartbeat signal to the name node. All the data nodes in the cluster, all n data nodes will send a heartbeat signal to the name node. So to indicate its live presence, if a name node doesn't receive a signal from a data node for 10 minutes consecutively, if a name node doesn't receive a signal, then the name node will decide that the data node is a failed data node. Then what happened initially, immediately it will mark that node as a failed node and it won't allow any further activity in that data node. Okay, once it doesn't receive a heartbeat signal consecutively for 10 minutes from a data node. So then once it marked it as a failed data node, what sort of action that it will initiate here is, here the name node will initiate the following action. It will look into the metadata. So what functionality a name node will provide? The name node will maintain the metadata information about this cluster. Here we have this information will be managed. File 1.txt is containing 3 blocks. The data node 1, we have 5 data nodes. Okay, like this data node 3, data node 4, we have 5 data nodes. Each I will make it with a separate thing. In this case, we have block B1 in this example is said to be stored in data node DN1, data node DN2 and data node DN4. Then block B2 was said to be in once again in data node DN1 and data node DN2 and let me make it under this data node block B2, data node DN3. So block B3 was said to be in data node DN2, data node DN3 and data node DN4. Okay, this is the initial information which is managed by FS image. The file FS image will manage this initial information. What happens here in this case? Once a name node detects, the name node will maintain the information in a RAM memory. Okay. So once a name node detects this data node fails, it will immediately look into the metadata. what are all the blocks that is stored on the data node DN2. Okay, in this case the data node DN2 hold three blocks, block B1, block B2 and block B3 in this example. So what happens here in this case, being the block being to have a 3 replica, now we said to have only 2 replica, that is a block is under replicated, it need to be resolved. Okay, so whether it is over replicated or under replicated is not a correct thing, we need to resolve the issue. So here the name node immediately look into the metadata to look what are all the data nodes which holds the copy of the block. In this case, it can find that the data node DN1, or let me make it first the block B1. The block B1 is stored in data node DN1. Now data node DN2 failed and we have another copy at data node DN4. So what it will do, the name node will instruct any one of the data node, either data node DN1 or the data node DN4 to make a second copy of the block. So here it will instruct data node DN1, you are having a block B1. The block B1, you replicate the block, you make a copy of the block into the data node DN3 or data node DN4. Like it will send the information. Once the data node DN1 receives the information instruction from the name node, it will make the copy of the block according to the instruction it is received. In this example, now we have data node DN3 holds the new copy. This information, block B1, is moved from data node DN2 because of corruption to data node DN3. This change is recorded in this edit log file. We have discussed the file by name edit log. This edit log file will contain the following changes. The original information will be with the FS image. Similarly, it will also decide under which data node block B2 and block B3 need to be copied. Now, you may have a one doubt. Now, so the name node, whether the block B2 can be instructed to copy on data node DN1? No, it won't copy in data node DN1. Also because, so it is already having a block copy here. We need to discuss this. So at any point of time, data node can have only one block copy. It can't have a second block copy of the same block. No data node in a Hadoop cluster will have a duplicate copies of a block. That means you can't have block B2 two copy in a data node. Okay, that is the first condition. So then the possibility here is you can have this block B2 copied into either data node DN4 or data node DN5. So that recording will be recorded. So block B2, now it is being the data node DN2 got failed, it moved on to the data node DN4. Okay, so this is the new area where we have block B2. So these informations will be registered in the edit log file, and the original information is in the FS image. Now here we come up with a problem called as data inconsistency. We come up with the problem data inconsistency. What do you mean by data inconsistency? Here the block B1 in FS image is said to be in data node DN2, data node DN1 and data node DN4, but whereas here in edit log it is recorded as data node DN3. Yes, same block is said to be occupied at the two different data nodes by these two files. So computer get a confusion. So which is the original thing. Here, how to resolve this issue? The data inconsistency issue. You have two different values for the same block. Okay, this is resolved by a secondary name node. We will, while discussing the functions of secondary name node, we will discuss this problem of data inconsistency. Whenever a failure of data node happens, will be resolved by the secondary name node. Okay, so here this session's intention is to make you aware how data node failure is known to name node and what sort of action a name node will initiate when it encounter a data node failure. Then what do you mean by block under replication? How the block under replication can be solved? These are all the interview questions you may face with respect to this topic. So what information is present in FS image and what information is present in the edit log? Then what is data inconsistency? Who is responsible for resolving the inconsistency? Is it clear for you? Okay. So now the name node So function that you have, what is the, so you have only one name node in your cluster. Okay. So the name node's responsibility is to maintain the metadata information about the cluster. The metadata information of the cluster. You know what is metadata. Okay, the number of data nodes, live data nodes, dead data nodes, the number of files, the blocks, number of blocks associated with the files, the owner, access permission, everything will be managed by the name node. Where the metadata will be managed, the metadata will be managed under the following two files. One is fs image and edit log. Okay, whenever there is a change, that change is recorded in edit log and the original data will be managed in fs image. In case of issues, if you face with this data inconsistency, in this case here this secondary name node will come into existence to resolve the inconsistency. Okay, so what happens if a name node fails? If a name node fails, in everything in the cluster will be down. The cluster will be down. You can't do any activity in a cluster. Okay, so this is the drawback associated with one.x, Hadoop one.x name node single point of failure. Please make a note. This is the drawback, the major drawback associated with version 1.x is name node single point of failure. If a name node fails, even though your cluster containing secondary name node, job tracker node, all data nodes are running, you can't do any activity. Why so? Because files, fs image and edit logs are files. It is not database, they are files. Okay, so if a name node fails, you can't do any action. Any action instance, you can't perform a read or write is not possible, and job execution is not at also possible. You can't do anything. So what you need to go for? So here we have discussed about this commodity hardware. We have discussed about this commodity hardware. So what is commodity hardware? Commodity hardware in sense low cost hardware. Now I come up with a question. Can we have a commodity hardware for our name node? So no. Why so? Because being it is a server, and if a name node fails, everything in your cluster will affected. So we couldn't have a commodity hardware for our name node. We need to have a little bit high-end hardware. We need to have a little bit high-end hardware for our name node. So it should have a facility to withstand a single point of failure. That means a server should have multiple processor, microprocessor 1, microprocessor 2. Similarly, it may have multiple RAMs, RAM slot, RAM 2. It may have a power supply 1, power supply 2. So in case of a processor fails, this processor will allow the server to continue its activity. Like we should have a hardware replication for our name node. Okay. So the commodity hardware is for only for the slave nodes, for data nodes only. So if a data node fails, no need to worry about. Since we have a 3 replica, we can able to continue our business continuity without any issues by looking into the data from the remaining replicas. Okay, that is the advantage of going for commodity hardware for data node. And if we go up with the same commodity hardware in the name node, it will affect the entire cluster. So because of the reason, you need to have a little bit higher end hardware for your name node. Okay. So now these are all the functions of associated name node. Now before going into that, I want to make a clarification, one small clarification. You have 5 data nodes. How these data nodes will be stored? The data nodes will be stored in a rack only. In a real time, you may have multiple racks. Okay, I can get the help of one picture now. You have multiple racks. So this is the way by which in a real time your machines will be accommodated in a rack. You know what is rack. Okay, so set of computers will be accommodated here. You may have a name node here. You may have a secondary name node here. You may have a job tracker here. Then you may have multiple data nodes, up to n data nodes. Okay, so here you have a file, the file.txt containing 3 blocks, block B1, block B2 and block B3. Okay, so here it is recommended to go for minimum 3 replica. Yes, is it possible to have a copy here? So block B1, block B2, block B3. All the 3 blocks is permitted to store on a single node. No issue. Okay, so let the data node. Either you can have block B1, block B2 and block B3 can be stored here. Okay, so now my question is, so can we have this copy of the blocks can be stored in this node? Is it possible? Is this scenario is possible? I have block B1 2 copies stored here and 1 copy stored here. Is it permitted? No, it is not permitted. So what is the reason behind going for this 3 replica? In case of a failure of a data node, to ensure this high availability, we go for this 3 replica. So if that is the case, if you have this block B1 and B2 copied on data node, let me make it data node DN1 and block B1 and data node DN2. So if this data node fails, what happens? You will lose both the data. Therefore, condition 1 is specifying that any data node can hold only 1 block copy. You can't have more than 1 block copies. You can have B1, B2, B3, all the 3 blocks associated with the file can be stored on a single data node. But this any 1 block cannot be, the second copy can't be stored in a data node. This is the mandatory condition. You can't store more than 1 block copy on a single data node. Yes, the second condition. Can I store all the 3 copy block B1 here, second copy here and third copy here belonging to a rack 1? That too is not permitted. So here minimum your data block need to be replicated against 2 racks. You need to have block B1 minimum 2 blocks of copy here and 1 copy need to be in another rack. Why so? Because since the rack is connected to a switch and a separate power supply, in case of a failure to the rack, even though if you have 3 block copies on these data nodes accommodated in the rack, you can't able to ensure if a rack fails, you can't able to access all the 3 copies because of the reason. If you have a copy across multiple racks, even though the rack one failure won't have an impact, then you can able to continue the activity by looking into the block B1 from rack 2. So these are all the conditions. Please make a note. This question was asked in an interview for an architect. Okay. So here the condition is you can have at any point of time only 1 block copy in a node. You can't have 2 copies of same block in a data node. The second thing, in a real time, so you should copy the block in such a manner that your copy need to be spanned minimum across 2 data nodes. How to perform this activity? Who is responsible? Now we are going to discuss. How to perform HDFS write and HDFS read we are going to discuss. Okay. So these are all the constraints. Now we are going to discuss about how this block write will take place. Who are all the components which involves in this block write. Okay, how to write a file into HDFS. Writing a file into HDFS. So we can get the assistance of the now you know what is HDFS client and you know what is a block. Also you know the functions of name node. Assume that these are all data nodes. Data node, data node, data node. These are all data nodes. You may have a secondary name node. Okay, you may have a job tracker. Imagine this is the scenario. Okay, this is your real cluster. Now, this file containing 3 blocks. The user can interact through this HDFS client. Then the HDFS client will interact with this Hadoop cluster. So togetherly, it forms a Hadoop cluster. Okay. So first step 1, the user RAM want to perform a write. He is having a file 1. The file containing blocks, 3 blocks, B1, B2, B3. So here when user submit a file, the HDFS client will based upon that default block size. So here the default block size is assumed to be 64 MB, and this file is assumed to be 192 MB. Therefore, this file is divided into 3 blocks, block B1 and block B2. This will be done by the HDFS client itself. Now the HDFS client want to find out the data node under which these blocks need to be copied. Step 1, what it will do is, this HDFS client send a request to the name node. Name node, I am having a file divided into 3 blocks. The owner of the file is Ram. He want to write the file into the HDFS. Okay, so into our cluster, he want to write the file. Then once this name node receives a request from client, client send a request to the name node. It receives a request from client. The name node will do 2 activity. It will refer into the metadata. Name node will refer into the metadata. First, what it will do, it will check whether the user RAM is having enough access permission. That is, he have enough write permission to write the file into the HDFS. Second, it will check whether the file 1 is already present or not. If it is already present in HDFS, there is no need to duplicate again. So these are all the 2 things that the name node will check with the metadata information. If everything is perfect, RAM is having access permission. Okay, the file is not already present there. Then in that case, the name node send a response to the HDFS client. Okay, you can proceed with this, and it will instruct the list of data nodes where the block B1 need to be copied. In this case, let me take, it will send a list data node DN2, okay, of rack 1, and data node DN1 and data node DN2 of rack 2. Okay, this will be decided. So where the block need to be written will be decided by the name node, not by the administrator or not by the HDFS client. Okay, HDFS client's role is to submit the forward request by the user, and the name node, it will aware what are all the information, what sort of data that is present in the data nodes, which data node is live, which data node is working, which data node is dead, all sort of information it maintained in the metadata. Okay, by looking into the metadata, name node will decide. So the list of data nodes where to write the copy, first copy of the block B1. So it will send a list. You, for the block B1, you write under the following data nodes. Once it receives the information, what client will do? The HDFS client will write the first block B1 into the data node DN2. Along with that, it also sends the list to the data node DN2. That the list it receives from the name node. Okay, the data node DN2, what it will do, once the block B1 is successfully written, the data node DN2 will make it into the list. Okay, now it receives the list, data node DN2 and data node DN1 and data node DN2 of rack 2. Okay, now it is a success. We have successfully written here. Then this data node's responsibility to copy the block into the second data node in the list, that is data node DN1 of rack 2. Okay, so it will make a copy here. Then it also send the above set list. The list will be sent by the data node DN2 to data node DN1 of rack 2. Then it is the responsibility of the data node DN1 to make a third copy. Now we have block B1 stored on data node DN2, data node DN1 and data node DN2 belonging to rack 2 and belonging to rack 1. So if everything is a success, what happened here in this case? We need to send the acknowledgement. The data node DN2 will send the acknowledgement. So to data node DN1. This write is successful. Data node DN1 send the acknowledgement to data node DN2. The data node DN2 will send the acknowledgement to HDFS client. The HDFS client will update this information to the name node. There will be like a chain of activity. Okay. So write also is in form of a chain. Acknowledgement is also is in form of a chain. Please make a note. So we call this as a pipelined write and pipelined acknowledgement. So this is an interview question. What is pipelined write? When a HDFS client receives the list of data nodes from the name node, it will send the first block B1 to the first data node in the list, and it is the responsibility of the data node to make a second copy, and it is the responsibility of that second data node to make the third copy. Similarly, the acknowledgement will be in a reverse order. This activity is similar to that of the flowing of water in a pipeline. Here it is designated as a pipeline write and pipeline acknowledgement. Okay, now similarly this process will continue for block B2 and block B3. So now everyone, after a successful write of all the three blocks, HDFS client will make this information notified to the name node. Now the name node will record the information in the metadata. So this is the way by which block writing will take place with the help of the name node and HDFS client. Okay, so any doubt? Okay, so I will let you know. So after a client, okay, so you can make it here. So what are all the things that we discussed? So we have this file. First, HDFS client will issue a create request. The name node will do all sort of things, and if it's okay, the user is having access permission and file is not present, the name node will send a list of data nodes. According to the list, block B1 will be written into the data node DN2. Now the data node DN2 want to write the block into the next data node in the list. Similarly, the data node DN1 want to write the copy the block into the next data node. Now it is called similarly all the blocks. So acknowledgement will be reversed back from data node DN2 to 1 and to here. Then once the block B1 is successfully recorded, now this process will continue for block B2. Similarly, block B2 will be occupied. At any point of time, we can find each block will be replicated minimum across these two racks. Okay, any block, it is a mandatory condition. So similarly, block B3. So once everything is succeeded, the HDFS client will record to the name node that the block write is successful. So this is the way by which block write will take place. Now we are going to discuss about how to perform a read, how to perform a read of a activity. HDFS reading a file from HDFS. Now the user RAM, once again the user RAM will submit a request to HDFS. So I want to do a reading of a particular file F1. Okay, please let me do the activity. The HDFS client, what it will do, it will interact with the name node. Name node, the user RAM is going to do some operations on the file F1. Kindly let us know the list of data nodes where to read the file. The name node once again will look into the metadata. Now it will have in the metadata block B1 is in data node DN2 of rack 1 and data node DN1 and data node DN2 of rack 2. These are all the information which is recorded in metadata. The name node it will check whether the user RAM is having enough read permission. It will check whether the file is already present or not. Okay. If we try to issue a select statement in our Oracle, select stock from employee, if the table is not present, it will let us know the table are view not found. Similarly, here if a user requests a file, if the file is not present, it will throw an error. So the user will be checked whether he is having a read permission, and the second check will be done whether the file is present or not. If both the thing is okay, the user is having a read permission, the file is already present, then what happens here in this case? So the name node will send a list to the HDFS client. So these are all the data node which holds the block B1. Now the HDFS client, what it will do? It will read the block from any one of the nearest data nodes. Okay. Now we have data node DN2. So which node is nearest? From that it will make a read of the data, and the data will be read and the information will be passed to the user. This is the way. It won't make a read on all the 3 data nodes. It will choose any one data node that will be decided by the name node. Okay, so that will be decided by the HDFS client, not by name node. Name node will simply send the list of all the data nodes. HDFS client will decide to which data node the block B1 need to be read, and it will read the information, and the information will be notified to the user. This is the way by which data reading takes place from a HDFS. Okay. So these are all the functions associated with the name node. So the client will decide based upon its response of the data node. Okay. So the client will get the information. The HDFS client will know what are all the data nodes. It will send a signal, and it know which data node is now free. From that data node, it will do the activity. That is not coming under our discussion. It will be inherently decided by the HDFS client with the help of this Hadoop framework. It is not the responsibility of the administrator or developer to decide. It is inherently built. Okay. Yes, this is the way by which reading and writing of file takes place in a Hadoop cluster. Next, we are going to discuss about the functions of secondary name node. We are going to discuss about the functions of secondary name node. What is the role of secondary name node? You have only one secondary name node. Okay, you may have more than one, but by default you have only one secondary name node in your cluster. Pradap, please mute yourself. So you have your name node. You have this secondary name node. The name node will maintain the metadata information into the RAM memory under 2 files. One is FS image, the second file is edit log. So if a name node fails, what happens in this case? You have a secondary name node and you have your job tracker, okay, under which you have multiple data nodes. Okay, so here in this case, what happens if this name node fails? Okay, so being this FS image and edit log, this metadata information being it is managed in the name node, if a name node fails, being the information present in the RAM memory is volatile. What do you mean by volatile? So whenever the power goes down, the information will be also erased. So because of the reason, what happens here in this case, the name node will lose the information, FS image and edit log information will be erased here. So when a name node recovers, okay, back, then this RAM memory will be empty. It does not hold any information. What happened here in this case is, here the name node need to know the status of the cluster at the time of failure. Okay, so in this case, the secondary name node, what it will do, for every 1 hour once, a secondary name node will take this FS image and edit log and it will make it as a backup copy in its hard disk. It is by default every 1 hour once. So what are all the information present in FS image and edit log? The secondary name node will read the information and it will make a backup of the information in its hard disk. Therefore, if a name node fails and during the recovery phase of the name node, the secondary name node will have the latest updated information, and it will have this FS image and it will have this edit log. Okay, then it will make a synchronization of edit log information updated to FS image, and the FS image will be copied into the RAM memory by the secondary name node. By the way, the secondary name node will help the name node in letting the name node to know what is the status of the cluster at the time of the name node failure during its recovery phase. Once the updated FS image from the secondary name node loaded into the RAM memory of the primary name node, the name node, by looking into the information from the RAM memory, it will now came to know the status of the cluster, and the name node will took charge of the cluster. This is the role played by the secondary name node. It is by default 1 hour once. We can, if we want to make it for 10 minutes once or 1 minute once, then it is the responsibility of administrator to decide what is the time interval. This process of copying the FS image and edit log and updating the content of edit log to FS image to create a new FS image by each and every hour is called as a checkpoint. This process is called as checkpoint. This process will be done by secondary name node. Then why the name node itself is not architected to maintain a backup copy? Since the name node, why is all the information, metadata information is recorded in the RAM memory, because all the nodes in the cluster, whether it is a secondary name node or job tracker or data node, send a frequent request to the name node, okay, requesting for information. If the name node maintain the information in the RAM memory, then it is easy for the name node to read the information and send back the response to the requested data nodes. If not, if the information, if it is managed in the hard disk, what happens here in this case? Being your hard disk, being it is an electromechanical device, it took some time to read the data and to present the data to the requested device, which may result in a slow retrieval of information, and in turn it will affect the entire Hadoop cluster. The performance of the cluster may be affected, and because of the reason, the Hadoop is architected in such a manner that to maintain the metadata into the RAM memory of the name node. So because the RAM memory is volatile, and if a name node downs, the information will be lost. In this case, the secondary name node, being it is having a backup copy of the metadata, it will make a copy of that backup into the name node's RAM memory, and by the way, it will help the name node in letting the name node to know the status of the cluster at the time of failure. Once the new updated FS image is copied into the RAM memory, the name node, by reading the information, it will now know the status, and the name node will take the charge of the cluster. This is the role played by the secondary name node, and this process is called a checkpoint. Once again, it is an interview question. Okay. So what it will do, you already know the FS image contains the old data. Let me make it here. The FS image, the block B1 initially was in data node DN1, data node DN2, and data node DN3. Let me take a small case. Okay. You have 3 data nodes. So let me make it to 4 data nodes. Data node DN1, data node DN2, data node DN3, and data node DN4. You have block B1, B2, B3 here. Okay. So now the data node DN2 failed. Now the block B3 is said to be copied under another data node. Let me make it the data node DN3. This information is regarded in the edit log. So in the edit log, the block B1 was moved from the data node DN2. Why so? Because the data node failed. Because of that, now the block is moved into the new data node, that is the data node. So let me make it data node DN4. Okay, this is the update. So this is the old FS image. This is the change made. What happened? The secondary name node will fetch the old FS image, and it will fetch the edit log, and it will update the old FS image by reading into the edit log. Therefore, data node DN2 will be replaced with the data node DN4. Now, after performing that, now we got a new FS image. New FS image. The new FS image will contain the updated information. Block B1 now stored in data node DN1, data node DN4, and data node DN3. Then this new FS image, the secondary name node will take a backup copy in its hard disk. Okay, and the secondary name node will replace in the name node we have this FS image and edit log, and in the name node it will replace this old FS image by the updated new FS image. This process happen by default every 1 hour once. Okay, so you can adjust the event to happen at either 10 minutes or 15 minutes or 30 minutes according to your requirement. So by the way, the secondary name node will help the name node in during its recovery phase of the name node if a name node got fails. So if a name node fails, there is no other option in Hadoop 1.x except your cluster will down. You want to wait. This is one of the major problem associated with Hadoop 1.x. This problem is resolved in Hadoop 2.x by having multiple name nodes. In Hadoop 2.x, you can have multiple name node. In Hadoop 1.x, you can have only one name node, and because of that, the name node single point of failure will lead to a downtime in your cluster. Then this is resolved using multiple name node. In this case, we have a primary name node and we have a standby name node. Standby name node, not a secondary name node. Both the name node will know the metadata. So here both the name node will know the metadata. If the primary name node fails, now standby name node now become a primary name node, and without any problem, your cluster will continue its activity. So this thing we will discuss during our discussion on Hadoop 2.x. So these are all the functions associated with the secondary name node. Now you know the functions of name node and the functions of secondary name node. Yeah, so the secondary name node is used to help the name node. What do you mean by single point of failure? Single point of failure means if any one of the component fails in a name node, the name node fails. If a name node fails, the entire cluster will fail. That is called a single point of failure. Okay, single point of failure means if a name node fails, even though all other computer in the cluster is working fine, yes, until then, until the name node has been brought back to the original condition, you can't continue any activity in your cluster. That is called a single point of failure. Okay, you have your computer, your RAM got corrupted. Can you access your computer until you replace with a new RAM? You can't able to do any activity. That is called a single point of failure. Okay, this is the one of the big problem associated with 1.x, and that is resolved in 2.x. Okay, so with this discussion, we have completed what we have planned for today's session. We have started up with the recall of what we did in our previous class, and we have discussed about this Hadoop architecture. So under Hadoop architecture, we have discussed about these blocks, how the data has been stored, what is the block size, what do you mean by block replication, and how to perform, how a name node identifies the data node failure, and what is metadata, and where the metadata has been stored, what is the function of name node, what is the function of secondary name node. Under that, we discuss about what is a checkpoint and how a name node failure can be overcome. Okay, using the help of secondary name node. Then we have discussed about how to perform a HDFS read and write. So these are all the things that we have covered in the today's session. In our tomorrow's session, our session will start at 7:30 a.m. tomorrow. 7:30, 8:30 to 9. Okay, tomorrow's session will be at 7:30 to 9 a.m. We are going to start with your Hadoop cluster. Okay, we are going to start with the concept on Hadoop cluster, that how to, what are all the associated hardwares, what we need to do in terms of installation. Okay, so if you are not available, you get the recording, no issue. So here tomorrow I am having a client meeting at 9. Therefore, our tomorrow session is restricted to 1 hour 30 minutes without break. We will continue for 1 hour 30 minutes. Thanks a lot for your patience. Okay, in case if you have any doubt, kindly let me know your doubt. From tomorrow, most probably, you may have a installation part of Hadoop cluster may be over. I will share you the recording by end of today evening. Thanks Abhilash, thanks Anis, thanks for Lalita and Pradap. Thanks a lot.